All right. So today we have Guhesh Kumaran, who will tell us about orthosymplectic quotient quiver subtraction. Take it away.
Well, thank you, Ulyss, and sorry for the technical troubles. So last time I gave a talk, I described quotient quiver subtraction, which was a way to gauge subgroups of the Coulomb branch global symmetry of 3D n equals 4 theories. And this was for the unitary case. In the time since then, we've made a bit more progress, and now I'm happy to tell you about orthosymplectic quotient quiver subtraction based on some work with Sam and Ami that we had last year. Okay, so the plan for today is very simple. I will start by reviewing some basic facts about 3D n equals 4 theories and also 6-dimensional theories with 8 supercharges. I will derive for you these quotient quivers very explicitly and then benchmark them against a few examples, one of them being nilpotent orbit closures. And then we'll see an application to 6-dimensional theories where I will show you how we found a magnetic quiver for E6 minimal conformal matter, and then I'll say some statements about future directions. Okay, so that's the plan. Firstly, about 3D n equals 4 theories. We have two branches to the moduli space. One is the Higgs branch, and the gauge invariant operators you should be thinking about are baryons and mesons, and they are subject to some F-term relations. So this is just classical physics, right? As a variety, the Higgs branch is a symplectic singularity, and there is a global symmetry this branch enjoys, which is the flavor symmetry. Now, if I take a theory and I want to gauge a subgroup of this flavor symmetry, all I do is introduce further F-terms, right? So this is, again, just classical physics. Geometrically, though, this operation of gauging the flavor symmetry is a hyper-Kähler quotient. Okay, this isn't the only branch to the moduli space of 3D theories. There's also a Coulomb branch, and this is slightly different. The object you should be thinking about here are dressed monopole operators. And unlike the Higgs branch, the Coulomb branch is quite different in the UV and in the infrared. So in the UV, it's smooth, right? And it enjoys an isometry, which is U1 to the R, where R is the rank of the gauge group. In the infrared, it may get corrected, and it turns out it becomes a symplectic singularity as well. And the global symmetry of the Coulomb branch may get enhanced to some non-abelian group. Now, unlike in the flavor symmetry case, it's unclear how I would gauge subgroups of this symmetry in field theory. And I'll further stipulate that we focus on the infrared. Nevertheless, it turns out that gauging this subgroup is also a hyper-Kähler quotient, and there's a nice way you can see this with 3D mirror symmetry. So here's how. If I start with a quiver gauge theory Q, and it has a mirror Q check, gauging the Coulomb branch global symmetry is precisely dual to flavor gauging if I look inside this 3D mirror. So this is the image. So it's literally, this diagram is reflected on both sides. The operation on the moduli space is a hyper-Kähler quotient. So when I gauge a flavor symmetry, it's a hyper-Kähler quotient on the Higgs branch by G, where G is the subgroup I'm gauging. And on the Coulomb branch, well, if I gauge a Coulomb branch global symmetry, then it's clearly hyper-Kähler quotient here. And then the dimension of the other branch increases by rank of G. Okay, so that's some review. Another thing I'd like to mention is this notion of magnetic quiver, and many people in the audience have been working with magnetic quivers for some time, and they appreciate why they're very useful things to talk about. And it's because it gives you an auxiliary description of a Higgs branch of a theory with 8 supercharges as a moduli space of dress monopole operators. And the best techniques we have to read them typically come from some brane systems. And they're very powerful because they incorporate non-perturbative effects that you may not have access to with a Lagrangian or something like this. And if I want to study the Higgs branches of these theories in higher dimensions, 4, 5, and 6, then I have a set of very simple combinatorial operations I can do in the magnetic quiver that will shed light on the structure of the Higgs branch in this higher dimensional theory. And I've listed some people, but this is a very incomplete list. So yeah, okay. Now, the key point is that gauging Coulomb branch isometry subgroups can also be realized combinatorially. And we've made a bit of progress on this in the past few years. The first thing that many people have worked on is this notion of quiver polymerization. And what it does is it gauges a UN or SUN subgroup of the Coulomb branch isometry of two disconnected quivers or a single connected quiver. So here we have what I call chain polymerization, where I take two quivers with gauge nodes 1 up to K, connected in some way. That's what the green line means, to some quiver which doesn't really, it could be anything. Another quiver Q2, which is connected in some way to this other leg of 1 up to K. And when I gauge them, I do a SUK gauging of the diagonal symmetry here. Okay. And I can do the same thing if I just have one quiver Q with two legs of 1 up to K. And there may also be some adjoint loops, as we had in either case. And this is called cyclic polymerization. And such a technique was inspired from looking at class S theories and gluing maximal punctures. So the picture you would have here is, if I have G of these guys, and I have a maximal puncture here, and I have a different G, then I can glue them up together like this. Okay, so this is where these things came from. Okay. A bit more pertinent to the discussion today is unitary quotient quiver subtraction. And this also gauges SUN subgroups of the Coulomb branch isometry. And the way you do it is by subtracting some quiver with negatively balanced gauge nodes. And I'd like to point out that using negatively balanced quivers is not actually a new thing, and we shouldn't be afraid of such a thing. So they've been used in a variety of contexts, such as introducing FI deformations of magnetic quivers, and also in decay and fission, they deal with negatively balanced quivers. But quotient quiver subtraction was inspired from gauging flavor symmetry subgroups in 6-dimensional theories. So we'll revisit this exact example a bit later on, but I'll just like to share roughly the philosophy of how this works. So there's this SP0 theory in 6 dimensions, and this means that there's no gauge, there's no vector multiplet, but we have a dynamical tensor multiplet. And at infinite coupling, this describes the moduli space of one E8 instanton. Okay, now I can gauge an SU3 subgroup of this, and I get a new 6-dimensional theory. But in terms of magnetic quivers, I replace the notion of one E8 instanton on C2 with this picture. So this affine E8 quiver is the magnetic quiver for this moduli space. Then I subtract this 1, 2, 3, 2, 1. So you can see how I just subtract the ranks place-wise like this, resulting in this quiver here, which is the Higgs branch of my 6-dimensional theory, which is SU3 times SP0. Okay. So that's where quotient quiver subtraction came from. And we'll revisit this again in a bit more detail. So apologies if that was maybe a bit fast. Okay. So techniques for unitary magnetic quivers have been very successful. We've had lots of success in finding techniques and developing the formalism that we would use to analyze Higgs branches of theories in high dimensions. For orthosymplectic quivers, we've had a little less success. But what I mean by this is there are some algorithms we have in the unitary case which do not extend so simply to the orthosymplectic. One example would be a way to identify the stratification of the moduli space. It isn't so clear how to do this with orthosymplectic quivers. And with unitary quivers, it is a bit more clear. One reason why orthosymplectic quivers are much harder to deal with is because it's a bit harder to identify the moduli spaces and their global symmetries. The key tool that we use to identify them, these moduli spaces and symmetries, is the Hilbert series. And this is through the monopole formula. The key difference with orthosymplectic versus unitary is this term here. So the monopole formula will allow for a full refinement of isometries in the unitary case, not so much for the orthosymplectic. So it's a bit harder to identify exactly what the generators and relations are in the chiral ring of the Higgs branch when you're dealing with orthosymplectic quivers. However, there are some alternative constructions if you want to really push for refinement, including gluing together whole Littlewood functions. Or if you're lucky, you have a brane system, and then you can argue for the identity of a Coulomb branch that way. Okay. So what are we doing today? We're extending quotient quiver subtraction to orthosymplectic quivers. So this analysis that I showed you before of taking the SP0 theory in 6D with 8 flavors and comparing magnetic quivers before and after gauging this SU3, we're just going to repeat that. And we're going to do it for different 6-dimensional theories. And the result of all of this is a collection of quotient quivers for unframed orthosymplectic quivers. So 6D is a nice playground for such a program, because anomalies constrain very heavily what subgroups of the flavor symmetry in 6D you can gauge. And so you can be very confident that the thing you find in the magnetic quiver is going to be something that generalizes very easily. Okay. So as I said before, the way you would read a magnetic quiver is through a brane system. So we'll be using Type IIA brane systems to read off magnetic quivers, and hopefully formulate a set of rules that apply quite generally to 3-dimensional theories. Okay, so I'll introduce a bit more notation. I guess this is notation that everyone is familiar with, but red denotes SO2N and not O in this case, and a blue means SP. So a circle is a gauge and a square is a flavor. And I'm using the notation where SP1 means SU2. Okay. So these are the nodes in a quiver, and you also have edges. We'll have 2 types today. One is by fundamental, just a solid black. And we'll also encounter bispinner matter, which I'll denote in red. Okay. Another thing that we need to consider is this notion of balance for gauge nodes. And this is really just a condition on the convergence of the monopole formula. So if I have a DN gauge node, which is given by a red circle, and it sees K flavors, maybe I'll write this down. So if I have DN and it sees K flavors like this, I define this quantity called balance, which is K minus 2N minus 1. And if this is positive or strictly greater than, if it's positive or 0, then I would say that this is positively balanced and balanced when it's equal to 0. Likewise, for a CN gauge node, the condition for this balance is K minus 2N plus 1 is greater than or equal to 0. Okay. Right. Take it, no questions right now. All right. As I said, we'll be using Type IIA brane systems, and there's a whole cast of characters that we'll see here. The most basic are the D6 and D8. So the D8 will play the role of some heavy branes, and D6 being like ones that end between them. You can also have NS5. And because we're feeling particularly ambitious today, we're going to introduce a host of O6 and O8 planes as well. Okay. So such a brane system has two important phases for us. One is the electric phase, which is when all the D6 branes end between NS5, and associated to this is an electric quiver. And the magnetic phase is when all the D6s end between D8s. Okay, and it's in the magnetic phase from which we will be able to read a magnetic quiver. Okay, so yeah, so the magnetic phase of the type 2A brane system is analogous to that of type 2B brane systems for 3D n equals 4 theories, where the D4 plays the role of the fundamental object here. Okay, because our D6s will be on top of orientable planes, it's also important to know what is the algebra, gauge algebra we read. So we have this table here. So if you have a minus, then you read D and D and so on. Okay, one additional point we'll make here is that we will allow for negatively charged D6 branes. So this is a formal thing which we will use in order to derive some magnetic quivers. I'll just write something here. Typically, when you have a separation of NS5, so the crosses are NS5s, there is an associated length, which is like the inverse gauge coupling. Now, when I have negatively charged branes, which denoted in red, we don't have such a thing anymore. So there is no associated tensor multiplet where there are negatively charged branes in a NS5 interval. Okay. Right. Any questions? Because now I'm just going to start deriving these quotient quivers for you. No. Okay, great. So our starting point is the following 6-dimensional SPK SQCD theory at infinite coupling. This -1 is some notation that F-theory people use. And if you're not familiar, or you don't have to deal with this right now, but this is the theory we start with. And it was shown that the magnetic quiver for such for the 6-dimensional theory is given here. So it consists of a chain of gauge nodes from D1 up to DK and back down with just a C1. Okay, so what's the strategy? The strategy is for different values of K, which will be 0, 1, and 2, you can gauge an SU3, G2, or SO7 flavor symmetry subgroup, right? So this is, again, just a condition from the anomalies. This is the only thing you can gauge. And then what we'll do is we'll read from the type 2A brane system, which was given in this paper by, well, Ami, Marcus, and then that was based off some work with Nopadol and Tomasiello, Ridelius, possibly someone else. And from this brane system, we'll just go to infinite coupling and compare the magnetic quivers. That's the goal. From which we'll derive quotient quivers for SU3, G2, and SO7, and we'll have to argue for the SU2 case because I did promise 4 in a slightly different way. Okay, so K equals 0 case. Now this was something that we saw before, but using slightly different magnetic quivers. So in this case, we still have SU3 times SP0, and I've written it in the way that we're still at finite coupling. So you'll notice that the flavor symmetry here is U1 times SP10. Okay, and you can see this in the brane system. So these are the D8 branes. This is the D6. This is the NS5. Okay. I've also just written the type of orientable plane we have here at the bottom, just for some convenience. And you can notice that we have negatively charged branes here. Okay, so some negatively charged D6. Okay, so I start with this brane system and I go to the magnetic face. So to do this, I just do a sequence of brane creations, and eventually I'll get here. So this is the magnetic phase of this brane system. So I try and move all of my NS5 branes, which were on the orientable plane, and I try to take them off. So we get to this phase and I read off a magnetic quiver. So you can see how on the minus here, I have one full D6, so I read D1. Here I have minus tilde, and so I read a C2, and so on for the D6s. When I have NS5s off the orientable plane, they each contribute a C1. You'll also notice that there's these minus tilde intervals with 0. So you could have a C0 like this. However, in terms of the Higgs branch from the monopole formula here, the Higgs branch of the 6D theory through the monopole formula, they won't really contribute. So I'm just going to ignore them for you.
What do they contribute in any case, the C0s, other than being able to read off some symmetry or something?
Yeah, I mean, this is it. So they contribute. So in the brane system, I need to have these so that I can read the correct flavor symmetry in the electric phase. But from the Hilbert series, no, I can't see anything. I don't see if they contribute anything at all. Right. Okay. So if you remember, this was the case k equals 0. So we had this chain of gauge nodes from D1 up to D4. Oh, I'm using the wrong. From D1 up to D4 and back down again with a C1. So this was SP0 with 8 flavors at infinite coupling, the magnetic quiver. And I just showed you what the magnetic quiver for SP0 times SU3 gauge theory is when the SP0 is at infinite coupling and the SU3 is at finite coupling. And I just compared them. And if you squint your eyes, you can see that there is a kind of subtraction I'm doing on this leg, which gets me from this quiver to this quiver along this arrow. And now I'm led to believe that I can gauge an SU3 in the magnetic quiver using the subtraction of this quotient quiver here. Okay, and I'll give details of exactly how you do this later, but this is just to show where these come from. Right. And then I just repeat. So what I did for k equals 0, I do for k equals 1. So here I have G2 times SP1 gauge theory, and it has a flavor symmetry of SO13 times O1. So you can see how the heavy D8s here give me the SO13 and the O1. Again, electric phase, I now do a sequence of moves to bring the NS off the orientable plane, and I go to the magnetic phase, which is here. I read off the magnetic quiver like this. And then once again, I squint my eyes to see how I get from here to here. And I'm led to believe that there's this G2 quotient quiver here. Right. And I do it again, k equals 2. So this time is a bit different. There's some bispinor matter, like in this red edge here. But the brane system is this one. I repeat. In the magnetic phase, I find this, from which I read off the magnetic quiver. And then comparing my initial SP2 with SO24, I have the SO7 quotient quiver. Okay, so that was G2, SU3 and SO7. What about SU2? Unfortunately, this doesn't come from the same argument. I have some argument where there is a natural Higgsing pattern in 6 dimensions, which goes from SO7 to G2 to SU3 to SU2. So this is the natural continuation of this sequence. it turns out that this D1C1, D1C1 is the SU2 quotient quiver, but it would be nice to find a gauging construction for this guy. Okay. But why did I stop there? What about larger groups? So here, for example, take SO8 gauge theory, and we'll put it on a -3 curve. Now, again, if you're not familiar with the language of F theory, all I'm trying to say here is that to cancel anomalies, you need to couple multiple types of matter to the gauge group. So for this case of -3, you need one vector, one spinner, and one co-spinner of SO8. So if I were to start, say, with some naive strategy where I have SP1 with SO20 and I gauge an SO8, I have to include these in order for my SO8 to be anomaly-free. So you can see that the transformation process from the initial quiver to the final involves two things. It's the gauging of SO8 plus the coupling of this additional matter. And that's the thing that complicates the analysis a bit more, precisely because of these bifurcations. The cases of SU3, G2, and SO7, you only had to couple one type of matter. So you literally just did a gauging. But this problem of adding additional matter is something that you'll face if you try and consider all SON for n greater than 8. So that rules out SO9, for example, from this analysis so far. And we have a lack of constructions for SUN and SPN. But I'd like to reiterate that finding systematic operations on orthosymplectic magnetic quivers is very difficult. So we'll take what we have. This is these four are enough to get some interesting results. Okay, so this is a summary of these orthosymplectic quotient quivers, these four here. Notice that each of them has gauge nodes with negative balance. So you can see this C1 from the formula I gave before needs to see 3 flavors, right? So it needs to see 3, but it only sees 1 and 1, which is 2. So this has balance -1. And this one's even worse because it has a balance of -2, right? Because again, needs to see 3. And all of these guys have nodes which have negative balance. So we can't identify what the moduli space is. And it's a bit of an open question as to what this is. In the previous case, when we had in the unitary 1 up to n and back to 1, you could argue that this is a monopole moduli space. So T star SL n. But here we really don't have much to comment about what the identity of these moduli spaces are. The second thing to note is that the total rank of the gauge nodes is dim G plus 1. So dim of SU2 is 3, and the total rank is 4, which means that if you want to subtract it, you need to rebalance with a C1 gauge node, or at least a rank 1. We'll see later that it kind of has to be C1. And we saw this before when we did our subtractions. So you can see over here, when I do my C5 minus C1, I get a C4, but then the D6 was missing 1, so I added it on top. Okay. Right, I've written the rules down, and it's not because I want you to read them. It's just to show that we have systematized it, and it does apply generally to 3D n equals 4 theories. Okay. So there is a maximal leg like we saw before. So that's the thing that you subtract off. So it'll always start something like D1, C1, D2, ... something. You obviously have to make sure that D-type and C-type nodes are aligned. I can't make sense of what a Dn minus a Cn is. And I just make sure that whatever I find at the end has nodes with positive rank and non-negative balance. And this is just so I can have something to compute at the end with the monopole formula. One interesting feature of quotient quiver subtraction, which we saw even with the unitary case, was that you can find unions of cones. Okay, so this happens when the quotient quiver is just long enough that you go past a junction, for example. So if I'm subtracting from this thing, and my quotient quiver is here, I can go up, or I can go across, for example. And both of these things are valid. Whatever I find, if I take the union, that will be the result from the gauging, from the hyper-Kähler quotient. Okay. Another feature of these rules is that we always gauge a symmetry with complete Higgsing, and we will not deal with cases where there's incomplete Higgsing of the symmetry. Okay. I mentioned unions of cones, so let's talk a bit more about that. They typically appear when you have a Higgs branch of a theory with incomplete Higgs. And the unions of cones in the Coulomb branch side manifests itself with these different possible alignments of the quiver, right? Okay. So that's okay. I can still compute Hilbert series. So if I have a union of n moduli spaces, then I just take a signed sum of the intersections of these moduli spaces. And the way I find these intersections is through some Kraft-Procesi transition.
But
Okay.
you can have several cones which intersect even if there is complete Higgsing, right? I mean, it's not the same thing. Or are the two? Are you saying the two are related, or did I misunderstand?
So I'm saying typically when there's incomplete Higgsing, you will find unions of cones. Maybe not exclusively.
Okay. I mean, there are many examples where you have complete Higgsing and unions of cones. And there are many examples where you have incomplete Higgsing and a single cone. I don't think, I don't know. I don't think there is data to say that one is the predominant case, but okay.
Okay, yeah.
I think
Or maybe,
relevant.
sure. I guess the way I was seeing it is that whenever I find that there is a union of cones from quotient quiver subtraction, then the resulting thing in the mirror necessarily has incomplete Higgsing.
I see, okay. So this is a conjecture you have. That is always true.
Yeah.
Maybe theorem.
Okay. Thanks. Okay, so if I have an intersection, I do some Kraft-Procesi transitions. In the unitary case, this is okay because we have some prescriptions for this involving subtraction of minimal degenerations. So this is the type of thing where you would subtract affine Dinkin diagrams, or you would have some slices like, well, I guess this is also affine Dinkin diagram, but these kinds of things which allow us to get the structure of the Hasse diagram. Okay. Unfortunately, such a thing isn't systematic for orthosymplectic quivers yet. So we will encounter unions of cones. So how will we deal with this? So it turns out it will be sufficient for our purposes to take this quiver C1 with two edges and use this for an A1 transition. So in the cases that we studied, we only found A1 transitions. So you will notice that both of these gauge nodes are C1. And the point is that when we find unions and cones in this thing, the alternating DC pattern in the magnetic quiver are explicitly broken. So this is a strange thing that we'll have to live with. Okay. Right. So I showed you this algorithm, but how will we actually check anything? So first of all, I said we were only restricting to cases with complete Higgsing of the symmetry. So if I have a moduli space which has an isometry G, M, and I can compute its refined Hilbert series, where T is the grading of the R charge, and this is some fugacities for the global symmetry G, I can gauge a subgroup G of Gm with a commutant G prime. So maybe I'll write it. With this Weyl integration formula. Okay. All I do is I take this Hilbert series I had here and branch the fugacities into G and G prime. So this is, these are associated to G prime. These are associated to G. And I just project out terms that live in representations which are symmetrizations of the adjoint of G. Okay, so if you like, this is an F term. And I can only have this formula because I have complete Higgs. Okay, and we'll just check the result from this quotient quiver subtraction algorithm against Weyl integration for some known moduli spaces. Okay. So this is what we'll be doing. We'll be graduating the nilpotent dojo. I'd like to credit Sam for coming up with this phrase. So shout out, Sam. This is the orthosymplectic quotient quiver subtraction kid, starring Jaden Smith. Right. Why am I talking about nilpotent orbit closures? Well, they're a very natural benchmark for any algorithms which involve quivers. This is because we know they're Hasse diagrams from independent sources. So if you wanted to work out, if you had some algorithm to work out the stratification, you can just compare it to something which has been well documented before. There are also very simple constructions of the Hilbert series. So we know this now. And we'll just use Weyl integration to compare to quotient quiver subtraction. So, okay, this is just a test of the algorithm, but is there any value in doing this anyway? Yes, because you get to understand.
A question about the Weyl integration. How do you, maybe you said this and I missed it, but how do you actually put in the refinement?
So this is a known moduli space. So I'm not getting this from the monopole formula.
You're not,
so
it's easy. You don't take a quiver and then extract it, but you take a Hilbert series that's refined.
I take a Hilbert series,
okay, fine.
So it's just a moduli space.
Understood.
Okay, cool. Okay, so so there is some merit to doing it.
Do you have any ideas for if you're now given some quiver and you want to do your quotients? Is this like, do you have some indication like how you can maybe partially refine to do this, or like is there any progress on this? Did you maybe go through like studying these quotients, maybe you understood something general here?
So for example, okay, so one thing is that we always subtract from these maximal legs, right?
Yeah.
And I don't really care what's here. I just ensure that the whole thing at the end is computable, right?
Yeah, we can say it's
it can be, I mean, this is just, well, because this is a maximal puncture, I can just replace this by a whole Litwood function, and then this admits refinement, and I can branch the symmetry in this, and I don't really care about anything else. So I can still check even when I can't, even when the moduli space isn't necessarily known. I just have to play a little trick using this leg as a thing. That's it.
Okay. So you say you know the nilpotent cone, and then you just glue this one in, and this one you can. Okay. Thank you.
Okay. So there's been a lot of work, especially relating moduli spaces of three-dimensional theories with discrete group actions on the as an after automorphism of the quiver compared to some discrete action on the nilpotent orbit. Then this was extended a bit more to continuous group actions. And here I should also mention the work of Andrew Dancer and the story with partial implosions. But here, the action of discrete symmetry is on a moduli space, and then its natural extension to some continuous group action gives you some new relationships between nilpotent closures. So in this case, under hyper-Kähler quotient. And yeah, so these are just new results that sometimes I don't think have been particularly well documented in the maths literature. Another nice byproduct of this analysis is that you get new orthosymplectic magnetic quivers for nilpotent orbit closures. Maybe ones that you didn't have a construction for before. Okay, so now I just have a bunch of examples to show you how this thing works. So the first few I'll show you will be verified from unitary quotient quiver subtraction as well, and then I'll show you an example which is you couldn't get from unitary quotient quiver subtraction. Okay, so I'll start with minimal E7, which is possibly a strange place to start, but we'll see why. If I branch my E7 symmetry into D6 and A1 using the following embedding, and then I quotient out the SU2, I'll find next to minimal D6. That's the result from Weyl integration. And if I did unitary quotient quiver subtraction, then this is the result I find, and indeed the Coulomb branch of this is next to minimal D6. Okay. But alternatively, I can take the orthosymplectic magnetic quiver for minimal E7, which takes this form, where I have this leg from D1 to D3, in fact 2, and D1 C1, and I take my SU2 quotient quiver, which was this D1 C1, D1 C1. So D1 minus D1 gives me nothing. Likewise, C1 minus C1. D2 minus D1 gives me a D1. And C2 minus C1 gives me a C1. Yeah. So notice that I rebalanced my D3, which lost one flavor, with a C1. So notice that this C2 here was balanced before, and now it has balance +1. And that's because it partook in the subtraction algorithm. So I didn't restore the balance of this C1, but I did for this D3 because it didn't participate. Okay, so this is the result I find when I do the subtraction process. Okay. And when I compute the monopole formula, we have some success because the Coulomb branch is next to minimal D6. And it turns out if I compute the Higgs branches of both of these guys, they're the same as well. Okay, but maybe this isn't too surprising because this is just an isomorphism between A3 and D3, right? So these are star-shaped quivers, and so I can just glue together the different legs. And so perhaps it's not so surprising that they give me the same moduli space as a vacuole. So this is a nice check that the algorithm we have works. Okay, maybe something a bit more non-trivial. So this time I'll go to minimal E6. Now I take the following embedding again. And when I do the quotient, I'll find next to minimal A5. And we know what the result is from unitary quivers. It's this guy. So when the Coulomb branch of this is next to minimal A5. Once again, I'll take a magnetic quiver for minimal E6, and I'll subtract this D1, C1, D1, C1. So these get killed. This D2 loses a rank and becomes a D1. This C2 loses a rank and becomes a C1. So both of these guys, this D1 and this D2, need to see one more. So I connect to C1, which joins them up like this. Okay. And then again, I find success because the Coulomb branch and the Higgs branch of both of these quivers here are the same. And this is a bit more surprising because I don't have any other construction which would indicate that this is the case. So I found some doppelganger for these guys. Okay. Let's do something a bit more exciting. Let's take a product of moduli spaces and gauge a diagonal subgroup. So unfortunately, I don't have any nice name for the resulting moduli space, but nevertheless, I can do the quotient with this embedding, and I'll find this Hilbert series here. Okay. And it turns out that this moduli space is the same thing as the Coulomb branch of this quiver, which you can find from some chain polymerization. So I'll review that quickly. What I mean is to join these two. Oops, I'm using the wrong thing. To join up these two, and you can see I get to this quiver here. Okay, so the Coulomb branch of this is this moduli space. Fine. But there are a collection of singly connected quivers whose Coulomb branches are products of nilpotent orbits. So this was given in this work by Marcus and Zheng Hao. And the quiver for the product of minimal F4s is this one. And I just subtract my SU3 quotient quiver, so you can see it here, and I end up with this result. Okay, so everything here up to the C2 vanishes, and then the D3 minus D2 is a D1, the C3 minus C1 is a C2, and then these D2s on the ends here need to see a C1. So that's my result. And they have the same Coulomb branch Hilbert series. So another nice check that this works. But unlike the previous cases, I can't evaluate what the Higgs branch Hilbert series of this is because I don't have a good field theory interpretation of what a non-simply laced edge is. But I don't have this problem here. So I can still evaluate the Higgs branch Hilbert series. So I'll leave it open like this, but it's nice that it'd be strange if the Coulomb branch matches, and then maybe this is some roundabout way to think about Higgs branches of non-simply laced unitary quivers through some doppelganger. Okay. Right, so this time we're going to find some unions because I think we've warmed up, unless there's any more questions.
Guhesh, what's the dimension of the Higgs branch in the previous case?
1,
1, 2, 3.
1.
It's maybe 2, but no.
Yeah.
It's 2.
Wait. 1. 1, 2. It should be 4, maybe.
4 complex. I see.
Yeah.
Okay.
Because we're expecting to go up by the rank. In
Yeah,
the
yes,
Higgs
it's 4.
branch.
It's 4. Yes. So and yeah, it might be one of the orbifolds. Could be an orbifold because the volume is an integer. I see. Okay, so we have we could try and check. Maybe the Shua knows this one.
Yeah, it would be nice to check. Okay, so now we'll see some unions of cones. So again, this is a result from the hyper-Kähler quotient with final integration. So I find it's a union of 2 orbits of A5. One is 2 cubed. The other one is 3, 1 cubed with an intersection of next to minimal A5. So it looks like this. This is 2 cubed. This is 3, 1 cubed. This is the next to minimal A5 that we had here. And they're related by Kraft-Pachesi transition of A1. Okay, If I do unitary quotient quiver subtraction, I will find these three quivers. So this one corresponds to the 2 cubed. This one is the 3, 1 cubed, and this one's the next to minimal A5. And this is just the intersection. Okay. Let's see what the orthosymplectic quiver gives us. So this time, if I go and subtract my quotient quiver, D1, C1, D2, C2, D2, you can see at the C1, I have a choice. I can either go up or I can go across. Both of them are fine. It's just I take the union at the end. So when I do a subtraction going up first, then these nodes are killed. This D3 minus a D2 gives me a D1. This C1 minus C1 gives me nothing. So maybe I'll do it a bit more slowly on the side here. So this is D1. Is this D1 here?
I think it's fine. I think it's very clear.
Oh, you think it's clear? Great.
Yeah.
Okay. Fine. So you just notice that I have this C1 doubling C1 here. So this is this is the first time we've seen here that you explicitly break the alternating D and C pattern. Okay. And then likewise, I can just go across. So in this case, I need to rebalance this C1 and this D2 simultaneously, which gives me this C1. And I introduce two edges because D3 minus, I subtract D2, 2 ranks from this D3. So I need to give it 2 more flavors, which is why it has 2 lengths here. Okay.
So here a line between two C's corresponds to a full hypermultiplet? Or to half, like the notation here?
Yeah, I think it's a full,
Like,
not
so
a half, yeah.
So how many hypermultiplets are associated to this double edge in this case of C1, C1? Is it 8 full hypers?
8 full hypers.
Like 2 times 2 times 2.
2 times 2 plus 2, yeah. Yeah.
Okay, thank you.
Yeah, that's right. Sorry,
Yeah,
maybe that
this
was
should be 4 hypers in total.
4 hypers?
Okay, so a line is still a half hyper, and that's
So
why
it's 2 and a 2.
Sorry. A line is still a half hyper, and I have 2 of them.
So that's why the double line. Okay, makes sense. So if you would start with a U2 quiver, which would have a single line, you could change them to SU2s, and then you would use this double line notation now.
Yeah, that's right. That's right. Sorry,
fine.
that was
Thank you.
Okay. Right. Okay. Now, because we have a union, we need to find the intersection, and that just involves subtracting this C1 quiver. So, okay, maybe it's clear to see here. If I subtract this C1, then all 3 of these guys need to be balanced with a C1, and I've drawn it in a strange way, but you get back to this quiver, which was the next to minimal A5 we saw before. Okay, so there's some self-consistency in this algorithm, which is good. And these are the doppelgangers we find. Again, the Coulomb branch and the Higgs branches are the same. Okay, any questions? No, great. So now it's time to take off the training wheels. Everything I've shown you before are things that we've seen before. So let's see something which you cannot get with the unitary algorithm. So we'll do it.
Well, Guhesh, the quivers with cycles in them are new, I would say.
I would say yes. I mean, in terms of the results in the moduli space, this is new, but as I said before, we have new constructions, new orthosymplectic constructions for these moduli spaces we've seen before, and the relationships under hyper-Kähler quotient. Yeah. So these are new.
Also, one other thing one can point out is that you have new examples of weak duality, where Higgs branch is the Coulomb branch. Sorry, Higgs branch is Higgs branch and Coulomb branch is Coulomb.
Yes. So these are all examples of weak duality because they have the same.
Is this just a standard IR duality, which is not 3-mirror symmetry? Or
The Higgs is Higgs and Coulomb is Coulomb.
yeah, so that's an IR. Yeah, but that's
It's an infrared duality, yeah.
U1 with four
it's not a
flavors.
3D mirror symmetry, but it's like
No, it's just an infrared. So they float at the same
so
infrared
an
fixed
IR
point.
duality. Okay.
Yeah.
Yeah, but also 3D mirror symmetry, the things flow to the same IR fixed point. It's just that like the notion of Coulomb
There's
and
a swap, yeah.
change.
It's
But
also swaps,
Yeah,
yeah.
so
there's a set
But
to
here
choice
it's
whether you're 3D mirror or not in an IR duality, but otherwise everything is the same, right?
So in one of them, you have weak coupling goes to strong coupling. And
Okay,
the other hand, you have weak, on the other one, you have weak
let's
coupling
call it
also.
weak. Mhm. Okay, thank you.
okay. So we'll take off the training wheels now. Here we'll take minimal E8 and we'll try hyper-Kähler quotient by G2. So we have a quotient for this, so why not? So if I plug minimal E8 and I use the Weyl integration formula, I'll find something a bit strange. I'll find a union of an F4 nilpotent orbit with the Balakata label A2. So if you like these characteristics that Rudolph uses, this is 2, 0, 0. And this orbit is 0, 0, 0, 2. So it's just another data for these orbits. It turns out that this one, A2 tilde, is a non-normal orbit, but the computation yields it's a union with the normalization of this orbit. Okay, so this is just what I find. The intersection of these two orbits is this one with Balakata label A1 plus A1 tilde, and they're related through an A1 Kraft-Purchase transition as before. Okay, so I'll choose the following embedding of F4 times G2 into E8. It's this one, where mu1 here, this is the 14 dimensional of G2, and not the other way around. So if you want, this is a 14 dim of G2. So what's strange about these orbits is they are height 4, this A2 and A2 tilde. So again, if you don't know what height is, for F4, it's defined in a simple way. I take this set of 4 numbers and I take the dot product with the Joule-Coxeter labels of F4. So these are the Joule-Coxeter labels. And when I dot this, these 4 numbers into this, what I get is the height. So 2, 0, 0 gives me height 4, and likewise 0, 0, 0, 2. This one has the following. So this is height 3. Okay. I'm highlighting this here because we don't have systematic constructions for nilpotent orbits of height 3 or more, even for the classical algebras. So there are Higgs branches in some cases, but like no magnetic quiver as a Coulomb branch. So finding constructions for these orbits are extremely rare. So let's do the quotient quiver subtraction. What do we find? So here the D3, D1 up to C3 will get killed. D4 minus D2 gives me a D2. The C1 also gets killed here. So I just rebalance this C3 with 2. So I have C1. Okay. And then the second alignment, again, I kill up to here. I have D2, C2, and I need to rebalance this C1 and D3 simultaneously. So I introduce a C1 where again, I have this double hyper between the C1s. Then to compute the intersection, I use my C1 double link C1 quiver, and I find this quiver with the loop. Okay, and this gives 3 magnetic quiver constructions for F4 nilpotent orbits, which we didn't have before. And 2 of them break the alternating D and C pattern of gauge nodes. So I'll summarize the results here. So we took the liberty of computing Higgs branch, and it's precisely the dual nilpotent orbit. So it's a slice from the nil cone to B3, which is a 21-dimensional orbit. And here, The Coulomb branch is the normalization of this orbit, but the Higgs branch is precisely the dual, the slice from the nil cone to the dual orbit of A2 tilde, which is given by this Balakota label C3. And again, we find that there is some symplectic duality between the Coulomb and Higgs branches. Okay, any questions? Because we're going to switch topic a bit.
So how much time do you want for your next topic? Because we're already a little over time.
Oh, this is the stuff about E6 conformal matter. So
maybe you
10
can,
minutes.
like, yeah, that's, I would then probably focus on reviewing and wrapping up rather than doing it in detail. You can show the results maybe.
Oh, sure. Okay. Well, that's good. Okay. Yeah, so this is just some background. The point is that there is a 6-dimensional theory which gives me E6 conformal matter, and this was inspired a bit from some F-theory constructions. So it's this gauge theory, SP0, SU3, SP0. And the separation of these fractional M5s controls the gauge coupling. And I want to try and bring all of them together. That's the picture that you should roughly have in mind. Okay, so first I do this pairwise and I get 2 half M5s, which corresponds to taking these SP0s to infinite coupling, leaving this SU3 at finite coupling. So this looks like a gauging of 2 E8 instantons. Okay. So, a construction that people have known before was to take 2 affine E8 quivers and then do polymerization. This looks okay. And you can write down a brane system for this, but it's unclear how to go to infinite coupling here. So attempts to go and find E6 conformal matter with unitary quivers kind of stopped at this point. Right, so we have an alternative way. We look inside Zheng Hao and Marcus's paper, and they have a nice quiver for a product of 2 minimal E8, 2 minimal E8s, which is this quiver on top here. And then I just perform an SU3 quotient quiver subtraction. So that kills up to here, and then I'm left with this. Okay, so this is still the point where SU3 is at finite coupling. If I compare Hilbert series for these two guys, I find that they're precisely the same. We're making some, we've at least matched what attempts have had before. Now, the last thing we need to do is to take this SU3 to infinite coupling. So in the brane system, I can propose the following, just based on this magnetic quiver. And now I just need to bring this NS5 onto the 08 minus, because that's the final way I can take the gauge coupling of the SU3 to infinity. So there's a small E8 instanton transition associated here. So maybe I'll go say a bit. So when if you like, we've collapsed these -1 curves simultaneously, leaving behind a -1 curve with the SU3 on it. So when I collapse this finally, when I finally collapse this, then I'll have a small E8 instanton transition, which is the way we'll go to, which is the final thing I need to do. Okay. Yeah, so it's precisely this. The shrinking of this final -1 curve to 0, to nothing, gives me all 3 gauge nodes at infinite coupling. Okay, so in the magnetic quiver, I just take this C1 and I slide it across, adding an affine E8 Dinkin diagram shape, and I end up with this result. Okay. And again, I can compute some Hilbert series, and you'll notice that this term, so these are some highest weight fugacities for E6 representations, where prime indicates one E6 factor compared to another, because there's two. So this is just telling me I have the dimension of the adjoint. Now this term is bifundamental of two E6s. And there's one relation because I can, there's a relation between the quadratic Casimirs of E6. So this is really bifundamental matter, which is exactly what you expect for E6 conformal matter. And this term is a biadjoint. And it's like I'm removing this bifundamental matter here as a relation in some sense. Okay, so Hilbert series seem promising. And then I can do the same thing and write down some brane systems for these. So here's the brane system in the magnetic phase and then in the electric phase, where I have this additional ON minus plane, which we didn't have before. I didn't introduce it, but this is what you need in order to get the brane system. Okay. This is also a class S theory with SO26 punctures. So I've written the puncture data here. So it's a strange quiver. It has different, I guess, avatars depending how you want to think about it. One says E6 conformal matter, one says a class S theory. Okay, I might just skip this because we don't need it and conclude. So what we found were 4 quotient quivers for SU3, SU2, G2, SO7. We applied them to nilpotent orbit closures and found some new constructions for F4 orbits and some orthosymplectic doppelgangers, which we didn't have before. We then applied it very quickly, I have to admit, to 6-dimensional theories and found magnetic quivers and a brane system for E6 minimal conformal matter. Some future questions are, how can we find more quotient quivers? So the method we applied now doesn't really work so much. So we need to find something a bit better. What about framed orthosymplectic quivers? So we didn't talk about those here, but we have some work with Sam and Ami, which is addressing this. And then can we find magnetic quivers for E7 and E8 conformal matter? And then this was a minimal conformal matter. You can also have rank N conformal matter, and how can we construct magnetic quivers for that? So I will conclude. Thank you. I'm sorry for going over time.
Right, so let's thank Guhesh. Do we have questions? So maybe you also mentioned this, but what's the problem with, I mean, it seems pretty clear the thing you subtract, right? Like these quivers, like why can't you just make them longer?
Well, we tried and we couldn't find consistent ways to do this. So sometimes you'll end up with gauge nodes which are negatively balanced.
Yeah.
And in this case, I can't really check whether the thing I found is correct or not.
You mean after subtraction?
After subtraction, the thing I find has gauge nodes with negative balance. So I can't verify the computation is correct or not. Right? So we really tried. Otherwise, we
to the thing.
would have had a family.
And do you do anything? Could you do anything that you can't realize in 60? Like quiver-based things that are not 60 operations?
Yeah. So I mean, if you just take so minimal E8, we played with a lot, and you can gauge SU2, SU3. So SU2, for example, is something you can't really do in 6D, right? Because that would be like, so that would be like SP0 with an SU2, and now I have E7. But the SU2 is no longer something I can have in 6D like this, right? Because it doesn't see the correct amount of flavors. So this is no good in 6D.
Okay, I see.
Yeah, so this is why the rules we have generalized to magnetic quivers in general, and it doesn't have to be something from 6D.
Very good. Do we have more questions?
One more point is this F4 case that when he was doing the G2 gauging of E8, minimal E8. This is it's not a 6-dimensional.
Sure, yeah.
Yeah, these are also not 6-dimensional. So yeah.
Okay. Very nice.
Which are, and you see also the nice thing is that you get new orthosymplectic quivers for orbits and slices.
Yes, yeah, that's cool.
Yeah. And that's one of the exciting things about this, that you try, you no longer are in 6 dimensions, but you still
Mimic,
some-
yeah, of course. That's the
Mimic
name
this
of the
thing,
game.
yeah.
It's a bit frustrating that these quivers show up so sporadically.
Yes.
This is really just
Yeah.
okay, good, nice.
Yeah, it's really a trial and error thing.
Yeah. Like
Once in a while you get lucky.
needle in a haystack. Good. Do we have more questions for Guhesh? If not, I'd say let's thank him again. And we can go off the record.